first speaker of this morning is Evelyn Buckwar from Heriot-Watt University, and she's going to talk about stability analysis to numerical methods applied to systems of SODEs.
Thank you. And first of all, I thank the organizers of this very nice conference for inviting me and giving me the opportunity to talk here. I will be talking about absolutely nothing, more or less, almost nothing to do with partial differential equations, only stochastic ordinary differential equations. And what I'm talking about is joint work with Colonel Kelly, who's in Jamaica, and Thorsten Sickenberger, who's a postdoc at Heriot-Watt University as well. So, some outline. I would like to give an introduction why on earth I am doing what I am doing, and perhaps even convince you that at the end of the day it does have something to do with partial differential equations. And I will talk a bit about stability for systems of ODEs and compare mean square and almost sure stability. And I will talk about mean square stability for linear systems of ODEs and compare Maruyama type and Milstein type methods. Okay, that's the guy. In general, well, one way to come to what I want to do is to start with a nonlinear stochastic ordinary differential equation. I'm a numerical analyst, so I want to apply methods to that. And obviously, I want to know how close the numerical solution or how faithfully the numerical solutions that I get represent the true solution of this system. And if I do a numerical analysis, then usually there are at least two types of stability that I encounter in this numerical analysis of numerical methods. Stability as such is a term like regular, kind of, you can use it on everything. Here for numerical methods, one type of stability that is usually encountered already in the convergence analysis, and usually also one of the things that PDE numerics would encounter kind of first, and I think there it's called Lax stability. This refers to the robustness of this discrete scheme to deal with round-off errors, so all sorts of other errors. So perturbations to the initial value and to the right-hand side of the scheme, if there is one. I mean, other than just a linear difference scheme for a linear partial differential equation. And if I measure that, and with measure I don't mean that I actually estimate that in any sense, but if I write down a definition of the stability, this involves the limit for the step size to 0 over a finite interval. And this type of stability, whether or not the numerical scheme can deal with round-off error, is necessary for convergence. So this is not the stability that I will be looking at. I will be looking at the other type of stability, Lyapunov stability, which essentially is simply asymptotic stability. So I perturb the initial values and want to know what an equilibrium or all perturbed solutions, whether or not all perturbed solutions go to this equilibrium or not. And in terms of numerical methods, I start with already convergent numerical methods and want to know whether or not the numerical methods represent or have the same stability behavior. So measured in this case, I take a fixed step size, because when I sit down and do numerical simulations, I have to fix a step size. I cannot let it go to 0. And I measure this with t going to infinity. The effects that has on numerical methods or in numerical methods are pretty different. So here is a geometric boundary motion. I have used a numerically unstable scheme. And what I have plotted here is the logarithm of the step size used against the logarithm of the L2 error between the solution, the numerical solution, and the true solution. And so for step size going to 0, this error simply explodes. So this is what I get on the picture when I deal with numerically unstable schemes. It simply doesn't converge, so completely useless. So I was pretty happy at some point to find out that this works for stochastic differential equations as well. Here we have an effect of the other type of stability. Again, geometrical motion with these parameters. So this is what in numerics would probably be called some stiff ODE. And there's a range of numerical methods, SPDF2. I'm sorry for the German. I hope this is nevertheless understandable. Explicit Euler, implicit Euler, the trapezoidal rule. These are multi-step schemes. And explicit Euler and the Adams-Bashforth, whatever they actually are, they're explicit schemes. And again, you have to read that from the left to the right. This is a logarithm of the step size going to 0. This is the logarithm of the error. And what happens is that these explicit schemes at the beginning for larger step size, they behave like the numerically unstable scheme. They start to explode. And only when the step size is small enough, kind of convergence kicks in. And then they do what they are supposed to do. And this guy essentially has a stability region of the 0 point. So it is convergent. One can prove that it is convergent, but it does never get the picture of the true solution right because of stability problems, weak stability problems.
Sorry?
Yes?
What are the two bad guys? Adam
That's explicit Euler and Adams-Bashforth, which is also an explicit scheme. So here you have restrictions on the step size. Only somewhere until up here you get the true solution. So in some sense that connects to the partial differential equations discretization. Usually the step size for, well, if I have a partial differential equation, I do a semi-discretization, I end up with an ODE, or here an SODE. And to the best of my knowledge, I'm not a PDE person, but correct me if I'm wrong, the step size of the discretization for the ODE is closely related to the step size for the space discretization. And if I have to choose that very small, I have to choose the other one also very small. And it would be nice to avoid that. So knowing something about this type of stability for SODEs, for linear systems of SODE, which is what I would look at, which might arise from semi-discretization of PDEs, I hope is also useful to this audience. So some background and some history on this type of stability analysis in stochastic differential equations. The background in ODE numerics is one does start with the nonlinear ODE that one wants to approximate, possibly. And what one first does is a linear stability analysis with this test equation, which simply comes by linearizing this guy, which ends up in this linear system with this Jacobian around the fixed point. I diagonalize this guy and have it decoupled, and then just have this nice scalar complex valued ODE. I apply my numerical methods to it and analyze the numerical methods. So far so good. Justification for a test equation. Now the same bit for stochastic ordinary differential equation. If I want to do exactly the same stuff, I start with my nonlinear SODE and want analogously do a first step linear stability analysis. I linearize around a fixed point. I end up with a system like that. These guys are only simultaneously diagonalizable if all of these commute. So this is a very strong condition on my just nicely linearized system. So the standard test equation is definitely not as justified as in the ODE case. Nevertheless, it has been, this is a history slide, has been used in various types of work to analyze several methods. And in stochastic numerical analysis, we have weak convergence and strong convergence, these methods and those methods. And mean square stability and all sorts of other stability. And one way or the other, all of these, or work on all of these have kind of point-wise come up. Most of them use mean square stability analysis of the corresponding methods, whether or not they consider weak or strong convergence. To the best of my knowledge, this was the only one which looked at almost sure stability analysis of this guy, and usually the theta Maruyama method, which is written over here. And they have looked at weak second order Hurikuta methods, so they had a large system of parameters for one and several noises. So this was a very long paper with pages and pages of stability conditions involving parameters over parameters. So essentially one does simply drown in parameters, and the insight gained out of that is approaching zero very fast. So this cannot be the idea to look at that, to find something else. So the goal of my work and my talk was to develop a systematic stability analysis, rather, justifying the choice of test equations. So obviously just the geometric boundary motion isn't enough. In particular, real life systems either already just modeled as SODEs or derived from semi-discretization as SPDEs. They have more than one noise and they are systems. And here it's definitely not clear as such under which conditions looking just at the geometric boundary motion as a test equation for giving qualitative insight of numerical methods has any results to, or anything to say for systems. Or at least that's a question, that was a question for me. Okay, just to recapitulate the types of stability that I look at. So when I talk about mean square stability, I use all the blue ones. So I perturb its initial values. This is just stable if it's bounded, and it's asymptotically stable if it's bounded, and this holds. And I'm talking about stability of the zero solution. And the same, of course, for almost sure stability, and all the same, again, also for the discrete systems. So that's what I use. So essentially, the most complicated bit from here to there is that f has turned to a and g's have turned to b's. Otherwise, I look now, I do not diagonalize anything. I look at these guys. And what I wanted to know in this part was whether or not it makes sense to look at systems when I compare mean square stability and almost sure stability. This was based on, or one of the starting points was a paper by Des Hayem, where he found that, let me go back for a second, in this paper, where he found that the Euler-Maruyama method in mean square could be astable, so I could or the theta Maruyama method, so I could choose a theta such that the numerical method had the same stability behavior as a continuous system, but this did not happen for the almost sure stability. And it turns out that this isn't a problem of the method, but it is rather a problem of the dimension of the system. So to do that, we did not look at the full system. Again, we did not want to drown, but we started to derive particular systems which would give us, provide us some insight. And this derivation is based on the stochastic stabilization and destabilization. So there are theorems by Mao and other people to start with a deterministic ODE and construct a diffusion term such that regardless of the stability of that, the stochastic differential equation or the zero solution of that is almost surely stable in with a chosen G, or almost surely unstable. So given some nice f, one can choose a g to do that. And in there is a constructive theorem which gives me exactly that. And what we have done was chosen these systems, starting with the idea that we are completely boring in the drift, simply because for numerical analysis for ODEs, where this is awfully interesting, work has appeared during the last 50 years. The question wasn't what do I have to do with that to have something interesting. The question was what do I have to do with that to get something interesting, even if I start completely boring on this bit. So this is boring, same parameter, keeps the number of parameters down. And here we have one system with diagonal noise which would stabilize the system, and I'll show you what this means in terms of conditions. And these are two ways to destabilize the system in the almost sure states. This essentially corresponds to rotating the flow of the ODE, and this is permutation going everything into the other direction. Okay, these systems are so easy to analyze that I more or less can get the explicit solution and immediately read F stability conditions, at least for mean square stability. So all of them are the same. So destabilizing noise simply means here that this enters positively. So if this is stable, I have to have this kind of more stable to account for this guy. And here I have stabilizing noise. So even if the original system, the deterministic ODE, would be unstable a bit, then I can add noise to stabilize the guy. And this is also the case in the scalar system. So the nice thing about that is that although I have systems, and actually I could have as many Wiener processes as I want, I have scaled them such that I get not pages and pages of conditions, but some which are simply look the same as in the scalar, which makes comparison with the scalar case more easy. Okay, once again the test equations, where we have put them together in one equation, applying the theta-Maruyama method, which is simply this one, to these test equations, we end up with difference equations like that. And of these difference equations, now we want to know the stability again. And using a result by Bellman on product of random matrices, where then the corresponding difference, the zero solution of the corresponding difference equation is mean square stable, if and only if the spectral radius of the matrices, or a certain matrix is less than 1, we get these stability conditions. So what you can see here is this is a bit which comes already from the continuous problem, and this as well. And this is a bit that comes from the numerical method. And this is exactly the same as in deterministic ODEs. If I have this at least 1/2, if I have this exactly 1/2, the only thing that remains is the condition for the continuous problem. If I have it bigger than that, I even have overdamping in the numerical method. And here the same. And again, all the scaling is such that it is easy to compare. And for the almost sure bit, we had to use a bit more stochastic analysis. So there are theorems based on discrete martingale convergence theorems, which help us analyze this, the almost sure stability of this stochastic difference equation. And essentially the same thing happens. In this case, we do only have sufficient conditions. This is this bit should be negative to have exactly the same stability behavior as the continuous problem, because in this bit it was stabilizing, here it was destabilizing. But here we have exactly the same condition as we had in the continuous problem. So although it's only sufficient, I would conjecture that we can have astability in this bit. So in contrast to, the property of astability, which simply means that I don't have to worry about step sizes. In the almost sure sense, this depends on the structure of the diffusion matrix and the number of noise terms, which is kind of the take-home message of this bit, regardless of all the funny conditions that were there. This is what is the outcome. In terms of mean square stability, as long as we only have a Boring drift as we started out here, only the noise intensity came up. So the structure did not have any effect on anything, which essentially means that already the geometric Brownian motion would give enough information in some sense, as long as this doesn't do anything. And it's one of the first times that something like that has been used for almost sure stability analysis. Okay, complete switch. We are looking just as mean square stability, but now we look at the influence of multiple noise terms on two types of methods. That is zero Maruyama method and the theta Milstein method, not zero, theta Milstein method. Again, we have to deal with these matrices. We're not going to get down to the nice test equation as the geometric Brownian motion. And to do that, just some awful notation. What we will use somewhere is a vectorization of a matrix, which just stacks these guys. The Kronecker product, so this is just to introduce a notation that we need. And there are some nice rules to deal with these vectors using the Kronecker product and vectorization. Okay, for mean square stability, I simply need the second moment of the solution and want to know what happens. And the second moment of the solution is, as is well known, given by the unique solution of this matrix-valued deterministic ODE. Okay, so what we simply do now is vectorize this P, and we end up with a large ODE with a large matrix, stability matrix in front of it, which is now just a deterministic ODE, but large, and we can, using our vectorization, the Kronecker product, write down the stability matrix. And from here we are back home and dry in deterministic analysis. We know, well-known result, the zero solution of this guy, of the deterministic ODE system, is stable if the spectral abscissa is less than 0. And the only thing to do is now plug all our matrices in there and compute. And we want to do the same for the discrete equation, so rewrite that again as our methods into this kind of guy, and we end up with a discrete equation in this form with this stability matrix, also after vectorization, vectorization, and the same result by Bellman gives us this condition. So the problem with, does it move? No, it doesn't. With the Milstein method is that at some point I need to or may need to simulate this double integral. If the Milstein method, if the system just has one Wiener noise, I don't. I can rewrite that in the usual way as in terms of the increment of the Wiener process. If this is commutative, I have the same nice feature and can rewrite that. Otherwise, I have to do a simulation, rewriting into some other form. And we have applied the structural analysis to all of these guys and have used the Caron-Loewe expansion as given in Kloeden-Platen to deal with this non-commutative noise. I just give one example here with commutative noise in here. So we rewrite that like that with all these interesting matrices over here. I might remark that one can of course plug all sorts of other numerical methods in here, but just by choosing different matrices. So this is not only for theta Maruyama and theta Milstein. And the stability matrix ends up being this guy. So these two guys are, if we go back, derived from the theta Maruyama bit, and only everything which is in C has to do with the Milstein bit. So our stability matrix can be compared to the theta Maruyama by just looking down here, and we see that there are more usually positive terms coming in over there. However, in general, of course, it is still awfully difficult to get the spectral abscissa or spectral radius of these general matrices. So we have followed the same approach again to choose some nice examples with few parameters. So with one noise, with two noises which commute, and with two noise terms which do not commute, and have applied the corresponding Caron-Loewe expansion to that, and calculated everything through, and calculated all the abscissa. MATLAB and Maple were kind of grounding for quite a while, and we end up again with stability conditions which look comparable to everything else. Again, these first bits are the same as in the original continuous problem, down here and down here and down here. The next bits are from the Maruyama discretization, here and here. And then for any type of Milstein equation or Milstein approximation, I have the diffusion intensities, the noise intensities to the power of 4 added in here. So the Milstein term is not really good for any stability conditions. In particular, if this is big, if these are big. So I mean, you would try to apply Milstein when you have a big noise. If you have a small noise, you can use Maruyama all the time, but they come in handy, or you would want to have them if these noise terms are big. But in that case, you may definitely run into stability, step size restriction due to stability. And one further example with a picture as well, or maybe actually quite early finished. Just a scalar guy, but with many noises. The theta Milstein method, the theta Maruyama method, theta Milstein method, where, as I said, we can rearrange this to this guy. And now the stability conditions compare like that. We again have here a sum of these 4 powers of the diffusion coefficients, which may be hard to get everybody here down to 0. And in particular, this guy depends on the number of noise terms. And one picture. So for arbitrary noise terms, this is too difficult to transfer into a picture. But we have chosen here all the noise intensities the same. So then the corresponding stability conditions simplified. And we can now plot the stability regions. So parameterizing x, the x-axis as the drift multiplied by the step size, and this by, due to the fact that they are equal, this is m times the square of the noise coefficient times h. So these lines correspond to the stability boundary of the original problem. So if I reparameterize to this guy, everything below that, for all the values of lambda and mu below that, the zero solution of the continuous problem is stable. And these almost white ones correspond to the stability regions for the theta Maruyama method for different theta. So this is theta equal to 0, a quarter, 1/2, where we get this trapezoidal method, and this looks like astability as we know it from the books. And further up. And the other guys correspond to the stability regions for the theta Milstein method, again for different thetas, and also for different m. So this is m equal to 1 or 2, which is coincides at here, m equal to 3, 4, and 5, and it would go down further and further. So the larger the noise, the number of noise terms is, the smaller the corresponding stability region for the Milstein scheme. If I look at school B and discretization of some SPDE, I think they had this nice sum cut off after 256 noise terms. I'm not quite sure, I guess this would be kind of somewhere down here. So just bear in mind, if you want to use the Milstein scheme, it may be pretty heavy on the step size. Okay, some outlook. We have started with very, very boring drift terms, just diagonal. If we add up some nice terms up here, so these are the so-called non-normal matrices, which may come up in PDE discretizations if one has advection, or may have advection PDEs, and all sorts of non-symmetric difference methods. And the question is then, well, as long as this looks like that, the stability of, if I delete that, the stability of this ODE, of this deterministic ODE, is still determined by the diagonal. So if this is negative, or if this is something else, the eigenvalues are negative, the guy is nicely stable. These guys introduce transients, so the solutions will look like that. So here I've plotted the second moments of each of the components of the methods, and these look exactly like those in the deterministic bit. So everything's nicely stable, but in the beginning all three of the, or at least two of these guys have a large transient. As I said before, in the mean square stability analysis, when the drift was very boring, only the noise intensity played any role in the analysis. Nothing happened if I changed the diffusion structure. But as soon as I start having these guys, and I have a different noise structure in there, so all the other parameters are the same, the scheme is the same, but it may be a bit wiggly, so I might use the same thing with 1 million paths instead of just a couple of hundred, but even then it's a bit bigger than the picture before. So suddenly, if I have non-normal matrices, the noise structure makes a lot of difference in the mean square stability of the system. So some summary, we have suggested A, the structural framework using this vectorization and getting a stability matrix with which one can work. We have started simply to look at what large number of noise terms or large systems, or how they behave under discretization. At the beginning, keeping the drift pretty boring and comparing mean square stability and almost sure stability, or the effect of multidimensional noise on two different methods. And it turns out that using simple systems which just encode one feature, this is actually possible instead of using large systems which theoretically should be used where one drowns in parameters. And further analysis goes into all sorts of pathological behavior. Of course, stiffness is the next big issue to investigate. Where again this nice stability matrix, which we have now for the whole system or for the whole numerical method, may come in pretty handy to encode stiffness in both kind of. It's made up of both the drift and the diffusion bit. And then we can look at stiffness on the whole. Okay, thank you.
Yeah, thank you very much. Are there any questions or comments?
Did you study the case of stuff?
No, I haven't yet.
Probably completely different. From the implicit in the light.
Yeah, it could be. The only thing that, or the only person I know who has one or two papers is Yoshio Komori. To the best. Well, I think the Baroviches have also, but not in this direction. So actually, the list of things one can do is pretty long. Yes, Stochastic, of course.
Any more questions? Okay, then thank you very much again.